Good morning, dear students. Uh, Last time I made a video of assembler pass 1. I am sure that you all have gone through it, and in fact many of you have gone through and have shown your interest in pass 2 of the assembler. Earlier we had pass 1 of the assembler. So just to remind you what happens in pass 1 of the assembler, there are certain tables which are created in pass 1, such as symbol table and literal table and symbol table, and then base table is structured. Mod table and pod table, as I told you, are the static tables, so they are not created, they are only made available to the assembler, right? So what happens in pass 2 of the assembler? Obviously pass 2 is responsible for object code generation, right? So pass 2 is responsible for object code generation. So in order to generate object code, we need to have some preparations, like symbol table is ready, base table is will be ready in pass 2 and will be used simultaneously parallel, and literal table is ready in pass 1. So all these tables, since these are almost ready or almost ready, so we can easily generate code in pass 2. Now there are certain things which you must remember before you process the pass 2 algorithm or the flow chart that has been given in Donovan's book, very good book. So before you go through the flow chart of pass 2 of the assembler, I must say that certain things must be remembered in order to properly understand the algorithm of pass 2. What are those things? First thing is the set of instructions, or better known as instruction formats. For example, this is the sheet, you can see. These are the instruction formats like RR instruction, RS instruction, RX instruction, SI instruction and SS instruction. These are the instruction formats, and these are the length of the instructions. This is very important. So every mod table has one of these type of instructions, every mod table, and the size will be mentioned in the mod table. And this is the object code format. Suppose, for example, if an instruction is of RR type, which is of 2 bytes, so its object code format will be like this. Simply the hexadecimal code of the RR instruction followed by the register 1 value, comma, register 2 value. Register 1 and register 2 value will be obtained from the either from the program or from the symbol table itself. Say again, for example, this RS type of instruction, RS is of 4 bytes. So its object code format will be like this. There will be 2 operands. First operand will be R1 and the second operand will combine 3 components. That is in fact the R3, D2 and B2. Wherever R's are mentioned, this means registers, and wherever D's are mentioned, these are displacement or offset. These are to be calculated in pass 2. Again, B's are for base registers. These are again to be obtained from the base table. As I mentioned, base table is structured in pass 1 and it will be prepared in pass 2. So once base table is made ready, this B's value will be obtained. So and then RX type of instruction has 4 bytes, and again you can see the first operand is register and the second one is combined with the displacement, base register and x2 2 is a subscript. So x is what? X means index register. So you can see these many registers values must be available before a code can be generated. What are the values? Either registers values, R's values, or depending upon the instruction format, or the value of D, or the value of D. D means the displacement. D will be computed once the symbol table, literal table and location counters value, everything is ready. D can easily be computed in pass 2. and then X can be obtained from the program itself. It's the index register. So from the program, if you go through the program, given program, you will easily get the value of X, and then value of B, that is base. So base register's value can be obtained from the base table, and base table is prepared in pass 2 and used in pass 2 simultaneously. So these things must be remembered. And then there are certain pseudo instructions. What are these pseudo instructions, and how they will be processed in pass 2? I remember I told you in my previous lecture that pseudo instructions are only assembler directives. That means they only give directions to what to do, rather than generating any form of code. But there are certain exceptions as well, as I told you also. What are those exceptions? Like DS and DC. DS stands for defined storage. DS stands for, DS is the instruction. DS, it stands for defined storage. And DC is another instruction. These are pseudo instructions. This is called define constant. So these two are those pseudo instructions, these two, but they take some bytes. So whenever these instructions come, location counter's value will be incremented. So please remember, these are the exceptional pseudo instructions, and there might be some more. So these instructions, whenever they are encountered in any program, if you see these instructions in any program, assembly program, definitely location counter's value will be incremented. And how the value will be incremented, by what amount? So for this you need to see the instruction in the program. For example, if it is written like this, DS to F, that means F, F means full word. Full word means 4 bytes, right? 4 bytes. So that simply means this instruction tries to get some storage of 2 full words. 2 full words. That means 4 into 2, that is 8 bytes. Location counter's value will be incremented by 8 bytes, right? Similarly, whenever you encounter DC statement in a program, you must see its argument. What is written after DC? It may be half word, full word, double word. So accordingly, the value of location counter will be enhanced. This will happen in pass 1, and based on this, the symbol table and literal table, etc. will be created. And another interesting thing is that how you will know that where are the literals in a program. How will you know? So in case you want to identify literals in IBM 360 or 370 machine, IBM 360 machine, so literals can be encountered when you see as an argument of any instruction this equal to sign, right? Whenever you encounter this sign, so whatever written after this, these all are called literals. So this will go into literal table. And all other symbols that are appeared in a program, all other symbols will be stored in the symbol table. So symbol table and their values I discussed in my previous lecture will be stored in the symbol table. Then literal table, the knowing which symbols are literals, I just told you. In IBM machine, a specific symbol equal to will be taken as a landmark, or will be taken as a identifier for the literals. So literals are stored in the literal table, and while creating literal table, there is an instruction called LTORG. What is that instruction? LTORG. This is called organized literal. So this instruction is responsible for creating literal table. Creating literal table. So this is all about some very interesting thing. Now, as I told you, base table is very important and is created in pass 2. So there are 2 instructions which are used to create base table. What are the instructions? One is using. These are pseudo instructions, and another is drop. So using is an instruction. Whenever this using instruction appears in a program, you are sure that now base table entry is about to be done. And what is the format? Using must have some arguments like this: x comma y, or x first argument followed by second argument. So the first argument give you the base tables, base registers contents, and the second argument will give you the register number, right? So whenever a using instruction is encountered in a program, base table value will be identified and stored in the base table like this. And whenever drop instruction appears in a program after a using instruction, whatever registers have been used for the base table will be dropped. These registers will no longer be made available. Now remember, in a program you may have a number of using instructions. It can have more than one using instruction. So if more than one using instructions are there, obviously it means base table may have more than one base registers. So which base register, if there are more than one base registers, then how or which particular register will be used whenever it is required. So for that we have to see that due to which using instruction a base table entry has been made, and how many using instructions are there in a program. So based on these two things, you may easily identify the base register and their contents. And what is the need of knowing the base register and their content? Just because, as I told you, there are instruction formats in which you need register value, displacement value, base register value, and index register value. So three things I have explained. Register value, R's value will be obtained from the program, right? And then displacement can easily be calculated, I will tell you, and then index registers value can be easily and directly obtained from the program, and then finally base register value, B's value can be obtained from the base table, and construction of base table, as I told you, is using the using instruction itself. So these are some basic and very essential informations which are to be kept in mind while going through the algorithm or the flow chart of PAS2. Now, after that, you can easily understand the PAS2 algorithm. So I request all of you to go through PAS2 algorithm of assembler and try to understand the algorithm. Now, if you encounter any problem anywhere while understanding PAS2 or while trying to generate the code of any given problem, please do let me know so that I can elaborate further through a video lecture or the text material. What's your way? Okay. So I hope you would have liked this brief lecture, and in which I have covered some very small and interesting and important points. So thanks a lot. Thank you.